record to the cloud. So I was thinking that today what I would do is I would hold on, I gotta bring up Moodle. What I would do is I would work one of the old exams. So I would work like an old exam too, and I'll just kind of like walk through. So it's going to be a smorgasbord of different types of problems. We won't do the momentum equation one because we haven't covered momentum equation yet. So we'll just skip that one. Let's see. Find a good exam. There's definitely an exam that, I mean, sometimes, some of these exams are great, and some of them, like, they'll have a question where I was like, oh, that was a mistake, or a mistake to include that on an exam. So let's see, let's try an exam two, a fall exam two. We'll do, I think, spring 2019, maybe. Yeah, this one has a very annoying third problem on it. I mean, not third problem, momentum problem on it, which was a mistake, but that's okay because we're not even gonna kind of get into that today. Hello, my Rocky pup. Okay, Rocky dog is gonna probably stick his nose in here and there today because he is feeling like, being annoying. So, all right, so we're going to start. So this is exam 2 from spring of 2019. You can find it on Moodle if you like. And let's see, let's share screen. We will do the whiteboard. All right, so I'm going to start. I'm going to skip the true false because everybody can just look those up. And if you have a question, you can just come ask me, how did I get this answer? How did I know this was true? How did I know that was false? So what we'll do today is I'm gonna start with number 2. So what did I say? Spring 2019 exam 2. And each problem has a purpose. It's like there to solve some particular thing. In this case, it kind of help you if you kind of figure out what it is that I'm going for. Anyway, so this tells you that an iceberg, it looks like berg is spelled differently. That's with an E. Anyway. Floating in seawater. So this is an iceberg is in seawater. So the seawater S equals 1.03. That's because of the salt. And the iceberg is S equals 0.9. So what percent of the iceberg is above the sea surface? So we want to know. So this is given. This is required. What percent of the iceberg is above the sea surface, above the surface. Okay, buoyancy problems are hard to write, and if you look back through all my old tests, they're all variations on a theme. And what I want to make sure that you understand is kind of this equation, because the equations are very, I don't know what the word is. The weight and the force of buoyancy are very similar, and so what I want out of you guys is I want to make sure that you understand how they are different. So I'm always kind of trying to find a way to drive at the difference between these two. So for example, in this case, here's kind of a picture of what's going on. We've got an iceberg, and it's got whatever shape it's got. And then here's the surface of the water. And the thing that you always learn about icebergs is you always learn that, most of the iceberg is below water. That's what they say always happened to the Titanic, is that they didn't see, all this, all the extra ice that was underwater, and that's what they hit. I have no idea if that's true or not, but certainly most of the iceberg is below the surface. So, and the reason for that is because these two numbers are very similar. Like the ice is only, I think I made that number up. I don't think I looked up the specific gravity of the ice, but the seawater is just barely denser than water. Water would have an S of 1, and then the iceberg is just less dense than water. And, I think I made that number up, but anyway, so it's because those numbers are so similar. So we have a free body diagram here, and it looks like this. Okay, we've got the weight pulling down on this thing and the force of buoyancy pulling up. Okay, so what we can say is, if this is the Z direction, so I can say the reason this thing is floating where it is because the sum of the forces in the Z direction equals 0. Okay, so that's just, basic statics. And so we've got two forces. The force of buoyancy is up minus the weight, which is downwards. Yeah, and it's, one of the hardest thing about this problem is you're looking at this and you're like, I haven't been given very much. There's almost no information in this problem. And so somehow it's got to come out of this, because that's the only possibility here. So the force of buoyancy is defined as the gamma. So basically both of these are gamma volume, and that's what makes this hard. But the key here is which gammas are we talking about, which volumes are we talking about? And the weight of an object has nothing to do with whether or not it's in water, or it has nothing to do with anything, right? It's like the weight of an object is always the gamma of the object. So in this case, the gamma of the iceberg times the volume of the iceberg. Okay, so that should be straightforward. But of course, in this circumstance, it kind of gets confused. And it just gets confused because there's kind of a lot of stuff going, because we've got this other gamma volume for the other thing. And so for the buoyancy, the gamma times volume, well, the gamma has to do with the fluid that's around it. So this is the gamma F. So that is what determines, so I'm going to call that gamma F, is the fluid that's around the iceberg. And then the volume that matters is the volume that is displaced. Okay, so that's the volume that would have that fluid but does not have that fluid. Okay, so there's the volume underneath the surface. And that's pretty useful because we're looking for the percent of iceberg above the surface. So if we know how much is below the surface, we can get how much is above the surface. So this is the volume, what we call the volume displaced. Okay, so that's the volume in red. So it does not include the volume in black here. Okay, and that's almost always what I'm trying to get you to understand when I ask these questions. Okay, so now it's like, okay, well, how do we drive at this? Well, we're just going to keep substituting. And I know I have some information right here. So this is S of the iceberg, and this is S of the fluid. Okay, so I can go and I can say, okay, well, the gamma of the fluid is S of the fluid times the gamma of the water times the volume displaced minus S of the iceberg times the gamma of water times the volume of the iceberg equals 0. And, we're getting alphabet soup, like each step, we're just getting more and more symbols. But I think we're also getting more and more things that, we know or that we're looking for. Because what's nice here is that gamma water algebraically goes away. And I can rewrite this, I could plug numbers in. And let's go ahead and do that. I think most of my students are more comfortable with some numbers. So 1.03, that's the gamma of the fluid, in this case, seawater, times the volume displaced, minus SI, so that's the specific gravity of the ice, okay, times the volume of I equals 0. So what's interesting here is that we can't really drive at we can't solve for the volume displaced. We can't solve for the volume of ice. However, I can solve for kind of like let's see, let's just do a little math here. Volume displaced equals 0.9 times the volume of the ice. Okay. And so what I can do then is I can rearrange this so that I get, let's just do volume displaced over the volume of ice equals 0.9 over 1.03, which if I plug into my calculator, which is a really nice thing to have, type it in correctly, equals 0.87387379. Okay, and so what that tells us is that the volume displaced is 87.4% of the total volume of the ice. Okay, so that's the percent that is underwater. So I could say this is the percent of the total iceberg that is underwater. Okay, and so that's kind of a nice, I don't know what the word would be, but that tells us exactly what we want. We want the percent that is above water. So we want the percent above. So that equals 1 minus the percent that's under, 1 minus 0.87379. So that equals, well, and then if we want it as a percent, we need to multiply by 100, right? 12. Right, so this will be 100%. And then, so I'd do minus 1 times, so it's 12.621, so percent. So 12.6% would be our answer here. So that's the percent above. Okay, any questions?
Yeah, I got two questions.
Sure.
For one, the circle you draw, like the vellum, is it look like American flag. That's looking good. That's a good one. The second one, so like, why do you flip like when you set up the equation 1.03 vellum display equals 0.9 vellum or the ice, like, and then you put them. So like, what you try to solve in there, like, why you have a vellum display over the vellum ice?
Oh, why did I end up going with the
Yeah,
volume displaced over the volume ice?
yeah,
Yeah. So what we're looking at is we're trying to find a percent here. We're trying to find the percent that's underwater or the percent above water, right? Either one. I mean, ultimately we want the percent that's above. So the percent that's above would be defined as basically this black portion. So that would be defined as, so the percent above would be defined as, I guess the volume that's above divided by the total volume of the ice. So that would be this whole volume. It's the whole volume of the ice, right? Now times 100%. So that's what we're looking for. But we can't really get at that because we don't have the volume above in any of our equations. But I do know that the percent below is defined as basically this bit right here, which we call the volume displaced. Okay, it could be just called, the volume below if you wanted, divided by the volume of the ice. Okay, times 100%. Okay, so what I recognize here is that these two quantities add up to 100%, right? So everything is either above or below. So I know they add up to 100%. So if I know one of these two, I can get the other one. So what I end up doing is I end up solving for this one because volume displaced is in my equations. So I basically kind of, I get to this point in the equation and I'm just kind of, at this point, I'm just kind of like wandering, like I'm just kind of like working with the equation. I don't really know how I'm going to solve this exactly. But then when I see I've got volume displaced and volume of the ice, I say, well, I can rearrange that and get this, quantity, the percent below. And once I have the percent below, I can get the percent above because those two have to add up to 100%. That's the rationale essentially. Does that help?
Yeah. Thank you.
I mean, it's a challenging problem only because the direction of the solution is not obvious from the beginning, right? It's like if you look at most of my buoyancy problems, I mean, they're all a little bit different. But a lot of them are very straightforward, and some of them you're looking for the percent above or below. And this is the only way to get at the percent above or below, especially if we don't give you one of those volumes. So you just have to kind of rearrange and try to get the volume above over volume of ice, or usually this volume displaced over the volume of ice.
So like basically, like if you would have solved just like either one of those, say if you would say like VI equal like 1.3 divided by 0.9 of the volume display, would it be the same answer or like would it be different?
I'm not sure I understand the questions. Repeat that.
Okay, I'm saying like, like you have the 0.3 volume display equal the other one.
Mm-hmm.
So if you would solve for any one of those, would it be the same answer? Like if you were example, like if you would divide by everything by 1.03.
Mm-hmm.
Oh,
you mean, so like, let's suppose right here I'd said, well, volume displaced equals 0.9 over 1.03 volume of the ice.
Yeah. Would it be the same thing stuff?
Yeah, I mean, everything would still work. Let's see, what would we do then? Yeah, I think what you could do from there, let's suppose you had solved it that way.
Yeah, that's what I'm asking. Exactly.
Okay, so then this is the volume displaced is, that's going to be, so the volume displaced, which is in red, V disp equals this number times the volume of the ice. So 0.87
Mhm.
379 times the volume of the ice, right?
Mhm.
So that means that this bit on the top, the black bit, the volume above, would be, it would be the remaining bit. So that would be 0.12621 times the volume of the ice,
Mhm.
right? Because these two, this one and this one, have to add up to the volume of the ice. So I would tell you that the volume above is 12%, 12.6% of the volume of the ice. So yeah, you could do it that way.
Okay.
Certainly. Okay. You could also have just said, I don't recommend always doing this, but at the beginning, you could have said, you know what? I don't want to deal with all this nonsense. I'm going to assume that the volume of the ice equals 1,000 not kilograms, meters to the cubic meters.
Mm-hmm.
And you could have just used that number all the way through. Every time you see the volume of the ice, you could put that in.
Oh.
And it'll work. Now, I don't always recommend that for my students because sometimes students don't know if that will work. In this case, it will work. And one of the things you could do to test it is you could work the problem twice, once with 1,000 and then once with 500 cubic meters, and see if you get the same answer. And if you get the same answer, you could feel pretty good about it working, So that's just an idea. So if you really get stuck, if you're like, there's just not enough information here for me to solve it, make an assumption. If the assumption is incorrect, then you'll lose the points for the assumption, but I'm still going to grade the rest of your work,
Mm-hmm.
But it'll allow you to do more work, right? So you don't want to get stuck. Like there's not enough information, so I can't work this and just lose all the points. You might as well make an assumption so that you can keep working.
Get some out of it.
What?
All right, thank you.
Okay. All right. Let's see. Next problem. Oh yeah. I'm on two screens. One so I can see your face, but of course you've just got your image. So let's see here. Clear my drawing. All right. So let's try. All right. So here's problem 3 here from that same thing. I love this problem, or problems of this sort. I can't remember. The level of the tank below is increasing. So this is problem 3.
Oh, that's the one.
And we've got a tank.
Yeah.
Okay. And you may note that I love these problems. Okay. If you look at enough of these things, you'll see that I rather enjoy this. Okay. So we've got this thing like this, and it's got a diameter. So one question that a lot of people want to ask me is, what is the shape of this tank? And if the tank has a diameter, you have to assume it's circular. Okay, the level of the tank below is increasing. So the level is increasing by 0.005 meters per second. If D is 4 meters, okay, so, and Q1 is 0.04 CMS. Okay, and I'm going to talk about some of the errors that I saw here. And then Q2 is right here. So I'm going to talk about some of the errors that I saw when I gave this problem. So the first error, and then it said, be sure to tell me if Q2 is into or out of the tank. So Q2 here is assumed out. Okay, so that means if we solve it this way and we get a negative number, that means it's actually in. So one of the things I'm asking from you to do here is, kind of just make sure you know what the answer means. Okay, so here's a control volume. Okay, I'm drawing it in red. Okay, and actually, I'm actually gonna change one bit of that. So here's the water surface. I'm gonna change this control volume and I'm gonna make it really big. Okay. So the way that I like to do these, so this right here, this is the storage in my system, in my control volume. And I've got this going in, so this is my Q in, and this is leaving, so Q2 is Q out. Okay, we could call it Q2 or Q1, either one. So Q1 equals, and this equals Q2. Okay, so what we're gonna do here, and the way I always like to think of this, I always like to think of in equals out plus accumulation. Okay, and that always, the only conserved quantity here is mass. So the mass in, which is rho Q in, okay, in, and I'm going to put it like this because there could be multiple ins, okay, equals, and I'm going to put it as a sum because there could be multiple outs. It just so happens there's only one out here, plus accumulation. And, you know, I usually say that the accumulation, well, we're basically saying it's the change in volume, okay, or excuse me, the change in mass. So in fluids class, we define mass as rho times the volume. Okay, and this is just a general equation that will work. So this is the law of conservation of mass. And in fluids class, we call it continuity. I don't know why they call it continuity. I think conservation of mass, while longer to say, is more, you know, with it. So the first thing we're going to note here as we work with this is that the density everywhere is the same. Like there's no changing density in this problem. So we're going to take these rows and we'll pull them all out. And once they're all out in front, I can eliminate them. Okay, so all the rows go away. Okay, so now I can say Q in, the sum of Q's in, there's only one Q in, so that's going to be Q1. There's only one Q out, so that's Q2. And then this is the change in volume. And so I need to define the volume. And the volume, in this case, this is a prismatic solid. So we just talked about this the other day. Prismatic solid, it has a constant cross-sectional area. So the area here is the same as the area here. It's the same as the area here. So what we do for that is it's always the area of the bottom times the height. Okay, and the area of the bottom in this case is pi times the diameter squared divided by 4. Okay. And again, this area is constant, so it can kind of come out here. Oh, wait, I forgot. This is delta mass, delta T. Sorry, I forgot about that. So this is delta T. Okay, so then our equation becomes Q1, which we know, equals Q2, which we're looking for, plus pi d squared over 4, which we know, times delta H over delta T. Okay, so in this case, delta H over delta T, I'm just going to kind of write this over here, delta H over delta T. Well, that equals dH dt. And hopefully you can see that this is a positive number and it represents, so this is the change in height over time of the water surface. So that is 0.005 meters per second. Okay, and hopefully you can see that. And so what we'll do is we're just going to go ahead, at this point, we just plug and chug. Okay, so we're going to get Q1 is 0.04. Okay, this, one of the big problems I had on my test is this is CMS. So people thought that's centimeters per second, but this is, if centimeters per second would be written this way, CMS is cubic meters per second. And one of the ways we know that is it's defining a flow rate. Okay, so it has to be it has to be volume per time. So this is cubic meters per second. And that was an error that I found pretty common on this problem. And then pi times this diameter, which is 4 meters squared over 4, and then dH dt, which is 0.005 meters per second. Okay, so let's go ahead and, oh, this should be a plus sign, sorry. So we can go ahead and solve this, and you know, I don't know what we're going to get here. Let's see, so pi times 16 divided by 4, so that's times 4 times 0.005. Okay, this number right here is 0.0628, so it's larger than this number. So basically that means Q out needs to actually be an in, or Q2 actually needs to be an in, because if we do the algebra, it ends up being negative 0.022831 or 32, excuse me, cubic meters per second. So then we'll say that Q2 equals 0.0228 cubic meters per second, and we had the wrong sign, so we're going to say it's in. Okay, and that's how we solve it. Okay, I will note that if this makes you uncomfortable, there is another way to do this, and I will solve that way real quickly. I'm going to use a green control volume. So this control volume looks like this, but this control volume Oh wait, let's, sorry, I went a little bit too far there. See if I can just erase the green. There you go. Okay, good. So this control volume, I'm going to go here. I'm going to end up well beneath the water surface. Okay, and so when I do it this way, okay, I'll work this one over here, and in equals out plus accumulation. Okay, and I get down, and so I say, well, I've got an in right here. I've got an out because we're still assuming that that's out. And what I've got right here is I've got an out right here, because what's happening is this volume right here is not changing. Okay, if I draw my control volume like that. Okay, so if I keep my control volume like stationary like that, so such that the amount of storage is not changing, then what happens is I've got an in, which is Q in. So I can say Q in or Q1, and I've got two outs, Q2, and I don't know what to call this other one. Maybe we'll call it Q tank maybe, plus Q tank, and I have no storage. The storage is not changing, so there's no accumulation. So this just goes away. So then for each of these Qs, I can expand it by making it V times A. And so Q1, well, we're not going to expand it because we know what its value is. So I'm just going to leave it as Q1. And then Q2, well, that's what we're looking for. So I'm going to leave that as Q2. But QT, I'm going to make V times A. V in the tank times the area of the tank. Okay. And so you should see pretty easily, hopefully, that this is the exact same thing as this equation right here. The volume of the tank, or excuse me, the velocity of the tank, well, that's how quickly this water is flowing upwards, which is 0.05. So this becomes 0.005 meters per second. And the area of the tank is pi times the diameter squared over 4. Okay. And notice that's the exact same as, if I plug in 0.04 cubic meters per second, you can see that this is the exact same equation as right here. Okay. It's just instead of having a dH/dt, we've got a velocity. And it's really just kind of like whichever way you want to think about this problem. Not too many of my students even bother drawing a control volume, just fine. But that's just kind of how you work this one. Any questions?
I got one.
Okay.
So I was actually going to do exactly the same way you just did, but like what I got confused, like it looked like the on the top is kind of like I didn't know that was supposed to be B2, because if I know, like, the one you just said, if I know the B2 was 0.05 whatever, I know how to find the Q2, but I didn't know that was supposed to be like Q2. I mean the BT like you just did.
Mm-hmm.
So like I just didn't know.
Okay. Well, you have a question about it now, or does it make sense?
Oh no, I'm good now.
Okay, good. All right, cool. All right. Then we will scroll down and we will get one of my exact favorite problems. So this will be number 5, or one of my favorite types of problems. I think I've actually talked to each of you. Well, I think Paul, we worked on this a little bit in the last problem solving session. And I think, Paul, we talked about this at some point. So let's clear this drawing. I'm gonna do number 5. I'm skipping over number 4 because it's a momentum problem. We haven't done momentum yet. We'll have a problem solving session where we just do momentum. And so, we'll kind of hold off for that. And so this is, anybody who's had my class knows I love Venturi meters. And I love them because they encompass everything that happens in fluids class. So I'll try to draw this as best I can. It matters a little bit, it certainly, let's see. That for freehand is about as good as I get. Okay, so we're gonna go like this. Oh, geez, okay. All right, off the screen a little bit. Okay, it's okay. All right, well, not perfect. I was so happy. That's what happens, hubris. All right, so we've got this thing right here. And we've got this thing down here, and we need some information. And so here's a diameter right here. I think it's 4 inches. And this diameter over here is 12 inches. It's starting to get tempting to just use inches all the way through, because this is 48 inches. Although 4 feet is certainly easier to use than 48 inches. We've got air up here, okay, which has a gamma of, looks like 0.2 PCF, 0.2 PCF. And then what's flowing through this? Water. So this is all water. So we know water has a gamma of 62.4 PCF. Okay, and then it tells us this angle is 30 degrees. I don't remember if we need that, but it seems like, it's always useful to know these things. All right, so then what they want to know is this is given, and what's required is the flow rate. Okay, these are my favorite problems. This is, of course, the whole point of the Venturi meter is to determine the flow rate through, somewhere. So basically, if you have a pipe and you want to know what the flow rate is, you just put a contraction in there and you measure the pressure difference between two locations in the pipe. Okay, so that alone tells us right now that our locations have to be at the ends of, we have to pick locations 1 and 2 if we're doing a Bernoulli problem, because we can't solve otherwise, because these are the 2 locations where we have information, and we have information because of this manometer. So we can kind of measure a pressure difference between those points like that. If I put a point up here, I don't know anything about the pressure there. If I put a point here, I don't know anything about the pressure there. So we can't just arbitrarily go somewhere else. So I like to think of Bernoulli as my master in these sorts of problems. You can certainly use a different equation as a master and plug into it, but I always use Bernoulli because it just seems like things plug into it easiest. And so it looks like this. Okay, and then one of the things that I do every time I do this, if I see a manometer, is I know that I can go from P2 to P1, I can create an equation. And so what I do is I bring the P1 over here by subtracting it out from both sides. So I end up with, I'm going to rewrite this again real quick, Z1 plus V1 squared over 2G equals P2 minus P1 over gamma plus Z2 plus V2 squared on 2G. Okay, and that's just an algebraic adjustment. And the reason we're doing that is because I know that I'm going to plug in for that, that quantity right there with the manometer equation. The other thing that we can do here, wait, what was it? Oh, so another thing to be aware of, I've got 2 fluids. I've got the water and I've got the air. The fluid that's flowing through from 1 to 2 is water. So that gamma is water. Okay, so we want to make sure not to plug in for any other gamma. Sometimes people will, when I see these things, will have an oil manometer or a mercury manometer, and people will plug in for the gamma of mercury there. So we want to just make sure that we understand what we're doing there. Okay, so that's my master. So as an aside, okay, I'm going to look at these quantities. And usually Z1 and Z2 come from the geometry. This right here comes from the manometer. And the velocities, let's see if we can get another color here. The velocities come from continuity. Okay, and ultimately that's what we want, is we want a velocity, because we know the geometry of this problem. So if we have the velocity, then we are good to solve. Okay, so here's my asides, and I'm going to think about each of these equations in turn. So, well, let's see here. So we'll start with the geometry here for Z1 and Z2. Well, I don't really know that we can do a whole lot here, but let's just go ahead and, okay, I'm going to make this the datum. Okay, I like to make my datum through the lowest point. And then that means that this one right here is just that height right there, whatever that is. We can make that, I think that's going to be Z2, right? Because if Z1 is 0, then Z2 is the distance above that. Okay, so that means that this one in red, I guess this one goes away. Okay, because it's the datum. And this one we're just going to keep as Z2. Okay, so kind of not helpful really, but you know, it will be. All right, so now we got to do, all right, so now we need to do continuity. Okay, let's see, we'll do blue for continuity. So geo z1 equals 0, z2 equals z2. Okay, another way to do this, like an alternate way to do this, is to just leave them as z1 and z2, you know, or z1 equals z1 and z2 equals z2. That would also work. You know, it's just, you know, I like to get rid of terms if I can. Okay, so continuity. Okay, so for continuity, I'm talking about inside this pipe, and I'm talking about the flow rate at 0.1 versus kind of what's going on at flow rate at location 2. So I can say the flow rate at 1, and let's go ahead and be clear about this because this is a mass flow rate to the mass flow rate. But because the densities are the same, I can get rid of those. And then I can say, well, Q1 is V1 times A1, and Q2 is V2 times A2. Okay, and at this point, I already know what this answer is going to be, but you can do this however you want. This is what a lot of students will do is they'll say V1, here's A1, pi times the diameter, which is 12 inches squared over 4 equals V2 times pi times 4 inches squared over 4. I do prefer to work in feet, but right here it doesn't matter because the inches are going to cancel with each other. So what happens here is the pi and the 4 go away, and you ended up with 12 squared over 4 squared. You could plug that into your calculator and get 144 divided by 16. Or you can note that this number, let's see here, this number right here is 3 times, so 12 is 3 times 4. So if we square them, the ratio is going to be 9 to 1. Okay, so the diameters are 3 to 1. So when you square them, it becomes 9 to 1. Okay, so what I recognize here is that V1, 9 times V1 equals V2. Okay, and you can plug that into your calculator and do the work. But what I do when I work these problems is I immediately, like, I don't even do all this work. Okay, so this is what I'm recommending to you. You sit down and you go, what's the ratio of the diameters? 12 to 4. Okay, the ratio of the diameters is 3, which means that in the narrow section, it's going 9 times as fast. So that means, so I can just look at this problem right off the bat, and I can just say, okay, so the narrow section, V2, is 9 times as fast as V1. Okay, so you don't have to do all of this work. You could usually, like if you followed my logic right there, you can do this right off the bat. Okay, and that gets rid of a variable up here in this equation. Okay, so basically instead of writing V2 up here, I'm going to write 9V1. So that's going to go in right there. The only trick with that is making sure that we square it, which means it becomes 81 V2 squared. A lot of times people will forget to square the 9. That's probably one of the 3 most common errors in this class. Okay, so now we're ready with the continuity. So then the last one is the manometer, and you know we don't really have a lot of space, so I'm gonna go ahead and put it here in green, which means I don't have a lot of space to solve this thing overall, but you know, such is life. All right, so the manometer, I'm going to start at 0.1, and I'm going to say P1 over, not over gamma, just P1. P1. Okay, and now I'm going upwards through the fluid from P1 up to here. Okay, so I'm going to say minus gamma. Okay, now I went up Z2. Now I'm going to keep going some distance I don't know. This right here is a distance I don't know. So I'm just going to give it a name. I'm going to call it H. Okay, plus H. And then I'm going to keep going from there all the way up another 48 inches. Plus, now I'm definitely going to want to use feet because the gamma is in PCF. So that's a gamma of water, excuse me. And so that's in pounds per cubic foot. So this needs to be in feet. Okay, so now I'm right up here. And what I'm going to do is I'm going to add, because I'm going to come back down, right? I don't care about this bit, but now I'm going to come back down. So I'm going to add gamma of air. And I'm suspecting on some level that the gamma of air, maybe I need to use that in this problem because it was given to me. So maybe we're not going to ignore it. We'll decide basically in a second, but gamma air. I came back down, what, 48 inches. So that's 4 feet. And I'm going to keep coming back down this much, H. So I'm going to say plus gamma water times H. Now, I don't know what H is. And that's going to equal P2. Okay, so that's the manometer equation. Okay, so as I always do with these manometer equations, I'm going to take this P1 and I'm going to bring it over to the other side. So this becomes minus P1. Oh, well, it's a little scrunched in there. So P2 minus P1. And then what I'm going to do is divide the whole thing by gamma water. So it's going to cancel this one. It's going to cancel this one. And this becomes gamma air over gamma water. Okay, so let's go ahead and write that out. And the other thing I'll note is I have a negative H right here, negative H right here, and I've got a positive H right there. So those are going to cancel. So I've got negative Z2 minus 4 feet plus gamma water over gamma air, excuse me, gamma air over gamma water times 4 feet equals this thing right here. So it's a little bit sloppy. I guess sloppy is not the right word. There's just an extra space right here. So that bothers my OCD. Okay, so, you know, if you've got an obsessive compulsive, you know, be careful of that. But the nice thing about this is we know all this stuff. Well, we don't know Z2, but gamma air over gamma water, we know, and P2 minus, so, you know, in this thing right here, we can plug directly into this equation right here. Okay, so we're going to go ahead and before we move on, I'm going to do gamma air over gamma water to show why we can ignore gamma air. So here's gamma air, 0.2 PCF over the gamma of water, which is 62.4 PCF. Okay, so if I do this on my calculator real quick, on 0.2 divided by 62.4 times 4 feet equals, so this number right here is 0.012821 feet. Okay, and hopefully it's clear here that when you compare this number to that 4 feet, that 0.01 doesn't really matter, right? It's 2 orders of magnitude smaller. More than 2 orders of magnitude, right? Smaller. Okay, so we do not need to worry about that that right there. So we're going to ignore this because it's small. Okay, if you wanted to include it, you could. There'll be no points taken off for that. It's just extra work. So usually what happens is when we go through these things, as we go from here to here, we see air and we just go, okay, we're not going to worry about it. The only way that you would have to worry about it is if this number right here were really large. Okay, like if that number were, I don't know. Well, the problem is it's always going to be small to this because they're the exact same number. But there are problems where the amount of air might be really, really large. Like if you have a problem and you're working in the atmosphere or something, you may not want to ignore it. So just something to be aware of. Okay, so we're going to plug these things in one at a time. And so we're going to go back up here. Z1 is gone. Okay, V1 squared on 2G exists. Okay, equals right here for P2 minus P1 over gamma water. We're going to take this quantity right here and we're plug it in. So we've got a negative Z2 minus 4 feet, and we're ignoring this bit. Okay, plus Z2. So that's nice. You see the Z2s are going to go away. And then we're going to say plus, instead of V2 squared, we've got 9V1 squared. Remember those parentheses over 2G. Okay, so what's cool here is that things are going to cancel out for us in a nice way. These Z2s are going to go away, as they always do. Note that we didn't need this 30 degrees. Okay, so that's a red herring. So maybe we can draw a little red herring right here. Be careful of those red herrings. And then we've got, so yeah, so now we're ready to go. I'm going to bring this 4 over to the other side. So I've got 4 feet. I'm going to bring this V1 squared over here. So I've got 81 V1 squared minus 1 V1 squared. So I'm going to get 80 V1 squared over 2 times G, which in this case is 9.81 meters per second squared. Okay, so that is very solvable. I'm going to take that squared off of there. Okay, and let's see if we can solve that. 4 times 2 times 9.81. Okay, divided by 80, it's about 1. Take the square root of that, it's going to be about 1 meter per second. Did I do something wrong here? I did do something wrong. Can y'all see what it is?
9.8.
Yeah, right. Yeah, so another very common error in this class. How embarrassing for me to do it myself, but you know, yeah, so this should be 32.2 feet per second squared, right? So 4 times 64.4 equals that, divided by 80 to the half power equals 1.7944 feet per second. Okay, and we take that, and there's no space, so I'm gonna finish it up over here, and I'll say Q equals V1 times A1, and so Q equals 1.7944 feet per second times the area, which is going to be pi times the diameter squared over 4. And so it's important that you use the same area as, so we're at V1, so we'll use 1 foot squared. Okay, and that equals, somehow it gave me red, and it's cutting off my image, but if we plug that in, we end up with 1.4093 CFS. Okay, so Q equals 1.41 CFS, cubic feet per second. Okay, questions? Thank you for the error catch. Hopefully that made sense. I even tried to color code this, which I always like the color code. I feel bad for people who are colorblind. Okay, good, because this is my favorite question. It will definitely show up. And I just love these questions.
I mean, it's even our homework, isn't it?
Yeah. I always assign one of these for homework specifically because I want you to be ready for it. But as I said, it's got geometry, which obviously matters everywhere in engineering, but it's also got continuity, manometer, and Bernoulli. So, I mean, this problem asks, it has all the things in it that I want you to know, from the course. Like if this was all you learned from the course, you'd be in pretty good shape. Not perfect, because we still need energy equation, but anyway. So I will clear this one. And we worked through that test very quickly. Oh, we've got a chat here. Oh, well, I don't know why your camera won't turn on.
So we've pretty much covered everything for the next test then, or is our next test going to be more than what this previous exam has on it, since it's going to be later?
Well, we did not do we haven't done momentum equation yet. So I have to decide whether or not that's going to go on equation 2, on test 2 or test 3, because momentum is hard. But usually momentum is on test 2, but also we didn't get to the force on the gates yet for test 1. So that's being moved to test 2. So it might be too much to put on test 2 to include momentum. I'll have to think about that. So it's just going to kind of depend. Anyway, so I mean, if you want to, you can look at problem 4 and you'll immediately go, wait a second, on this test, you go, wait a second, we haven't seen any of this. Not to mention that was an exceptionally long one. I didn't mean to make that one that long, which was an error on my part. So anyway, let's try another test. Let's see if we can find another exam 2. Let's see, exam 2, fall 2018. Let's try. So this was the first semester that I taught it. Oh, yeah, okay. This is pretty good. All right, so this will be exam 2, fall 2019, number 4. This will be a continuity problem. Okay, and this is a pretty hard one. So the continuity problem I did on the last test that we just worked was probably the easiest continuity problem I've ever given on a test. This one right here is pretty difficult, and it looks like this. We've got a pipe coming in. We've got what they call an ideal mixing chamber, which whenever you see the word ideal, think this does not exist. But you know what I like about all of this, with all of fluids and all of these classes, is the problems can get harder. But as long as you understand the kind of the basics of the problem. So this is the ideal mixing. I mean, the basics. As long as you understand the equations, anything can be solved. So the ideal mixing chamber, and what the ideal mixing chamber means, you know, is that the second things arrive in that chamber, they are mixed. 100% completely mixed, et cetera, et cetera. All right, and they've given us arrows. So this is going this way, this one's going this way, and this one's going this way. Okay, so in this ideal mixing chamber, pipes 1 and 2 have a 4-centimeter diameter. Okay, 4 centimeters, very nice. We get back to the metric system or the SI system, and pipe 3 has an 8-centimeter diameter. Okay, that's a little bit, you know. Okay. Alcohol, alcohol enters through pipe 1 at 1 meters per second. So we've got 1 meter per second, and it's got an S of 0.79. While water at 10 degrees Celsius enters section 2 at 2 meters per second. So we've got 2 meters per second. And what's entering is, so this has S of 1 because it's water. Okay, we just say that this is water. This is alcohol. The level in the cylindrical tank falls at a rate of 10 to the minus 4 meters per second. So this thing is kind of, I don't really know how to draw this, maybe like a squiggly line of, so that, now I'm just going to go ahead and label that as dH/dt because the height is changing in time at, what did it say? 10 to the minus 4th, 10 to the minus 4th meters per second. The combined mixture of alcohol and water has a specific gravity of 0.86 and leaves the tank at 3 meters per second, 3 meters per second. Okay, so that down here, S is 0.86. That's because it's an ideal mixing chamber. The second it makes it into here, it's all mixed up. Okay, assuming immediate and complete mixing of fluids, determine the diameter of the tank. So we want to know, what is the diameter of this, the top of this tank? Okay, and like I can't even draw that diameter, but I guess if I could, maybe it would look like this. Right, and so the diameter would be from one side of this to the other, you know, and imagine that's a circle. Okay, so what's interesting to me about this is a hard problem, a hard, what do you call it, problem, continuity problem, but ultimately it's not really any different from what we just did. It's just that, like, for example, the density doesn't cancel out because we have different densities in each pipe. So I can say in equals out plus accumulation. And I need to decide which way I want to think about this. And so in this case, I'm going to do my control volume as the tank itself like this. And I'm going to go pretty big here. Okay, I'm going to go well above my water surface so that the water surface dropping, that is a change in accumulation. So this is accumulation. You could think about it as velocity times area if you wanted to, and you would just do your control volume where it kind of topped off below that. Okay, and then you could just think of it as, you know, instead of thinking of this as dH/dt, you can think about that as the velocity leaving the tank, right? If you wanted to, or leaving the tank. All right, so I've got in, and I'm going to do each one of these in turn. So let's see. Well, actually, you know, I'm just going to write it as this: the sum of the row times the flow rates in, and it looks like I got 2 of those, equals the outs, the sum of the row Q out, and it looks like I've got 1 of those, plus the accumulation, which is going to be the change in mass, rho times the volume, over time. Okay, and really, like, you know, we could make this a derivative. Okay, and so so now we have to do this for each of these things, and I'm just going to I'll circle them in blue as we finish them. So let's start with this n. Okay, so that's going to be S. Well, here, let's expand this. Let's not expand it first. Okay, so that's going to be rho 1 times Q1. Okay, that's going in, plus, and then we got to do this one, which is going to be row 2. Oh, well, I didn't necessarily want blue here, but whatever. Row 2, Q2, that's in. Okay, now what's going out? Well, I guess that's row 3. Is this, oh yeah, this is a 3. Okay, there's a 3 here. Row 3, Q3. And then plus, and now I need to think about this d rho v dt. And this row right here is unchanging in time because they told us that. Kind of interesting. It would in fact change in time, but in this case, we're going to bring it out. And so we're going to get rho tank. Okay, now this volume here, remember that's the area of the bottom. Okay, so that's area of the bottom times the height of the water. So that's H going this way. So the area is not changing, so we can pull the area out, the area of the tank, and we're left with dH dt. Okay, and so now we're cooking with gas. The last thing we need to do here is that this row 1, I'm going to make S1, in this case S alcohol, times the row of water, Q1, plus gamma row 2, that's S2 row of water, times gamma Q2, equals, this is going to be S3 row of water, times Q3. And this is the row of the tank, which of course is the same as what's leaving down the bottom. So that's going to be S3 times the area of the tank, which is what we're solving for, times D. Oh, I forgot my row water. Times row water times the area of the tank times dH dt. Okay. And what's nice is, and that's one of those moments where it's really nice to use the specific gravity because all these row waters go away, which is pretty nice. So at this point, this is just a plug and chug. So S1 is 0.71 times Q1, which is, oh no, we have to do V times A. Sorry, forgot about that. So this should be V1A1, this should be V2A2, this should be V3A3. So this will be V1A1, V2A2, V3A3. And actually, you know what's gonna make our lives a lot easier is I noticed that for any area, that's pi over 4 times the d squared, which means every one of these areas algebraically, it has a pi over 4 d squared on it. So the pi over 4s are going to cancel through this whole thing. Hopefully you guys can see that. So what I'm going to do here is I'm going to go ahead and write in the, so V1 is 1 meter per second. In the area here, I'm not going to bother with the pi over 4 because they're going to be a pi, well, you know what, I'll just put the pi over 4 in there, it's no problem. And then d squared. So this will be A1 squared, which is, oh, what are you doing? Don't do that. I didn't want that. Go away. Stop doing that. Can I get back to, there's my, I don't want my, no. Sorry, somehow I hit something and it won't let me unhit it. Return, done. Got it, go away. No, we're doing Zoom here. I don't want anything. Okay, here we go. Good. All right. All right. So then this is 0.04 meters squared. And here's S2 is going to be 1. So that goes away. Times V2, which is 2 meters per second. Times the area, which is going to be pi over 4. Times the diameter squared, which is 0.04 meters squared. Equals S3, which is 0.86 times 3 meters per second times pi over 4, that's the area, pi over 4 times what's the diameter there, 0.08 meters squared. Okay, plus S3, which is 0.86 times the area, which is pi over 4 times the diameter of the tank squared, that's what we're looking for. DHDT, which is 10 to the minus fourth meters per second. Okay. So hopefully you can see at this point that these pi over 4, because it's in every single one of these, is going to go away. Okay. So now we just have to do, we're going to kind of, take up some more space up here. Let's go ahead and I'm just going to do term by term, 0.71 times 0.04 squared. So this first one is 0.001136. And the units there is cubic meters per second. And we'll add, we've got 2 times 0.04 squared, 0.0032 cubic meters per second equals, so I'm going to do this one, 0.86 times 3 times 0.08 squared equals, let's see, 0.016512 cubic meters per second. Okay, so far that's the dominant term, is what's leaving. And then this one right here, plus let's do 0.86 times 10 to the negative 4. 0.86, well, we know times 10 to the negative 4. I don't know why I'm typing this in. Anyway, 0.000086. Okay, and the units on that are meters per second. Yeah, times dt squared. dt squared. Okay, so the dominant thing that's happening here is the water is leaving here. That is more important, far more important than what's flowing in. Okay, which of course explains, why this is dropping. Okay, so let's go ahead and solve this. Oh yeah, that's right. So the mistake I made here is that this needs to be a negative dHdt. So down here there needs to be a negative sign. Okay, because dHdt is negative because it's going downwards, because the change in the height is negative. So what we're going to do is we're going to make this a negative right here. Okay. So yeah, I kept staring at that one. This isn't going to work mathematically. All right, so then we'll go ahead and say 0.001136 plus 0.0032, and we'll subtract 0.016512 equals that number. Oh, wait, this is CM. Oh, that is a CMS. It just looks ugly. CMS. Okay. And then we'll divide that by this number, divided by 0.0000. Oh, those are decimals. 1, 2, 3, 4 zeros, 86 equals, so dt squared equals 141.58 meters squared. And so we take the square root of that. Oh no, don't do that. Okay, it's giving me too many errors. Anyway, 141.58 to the half hour. And we get what? dt equals 11.899 meters, or dt equals 11.9 meters. Anyway, that's how we solve that. Okay, questions? I want to go through my solutions and make sure that I work this correctly. Yeah, I got 11.8 meters. But I think I had a rounding there.
Yeah, you also had 0.71 instead of 0.79. I don't know if that makes enough difference to make that.
It might make the difference between 11.9 and 11.8. Thank you. That's a good point out. If you saw that earlier, I wish you'd have told me. But anyway, that would make this number slightly larger. I'll go ahead and do the calculations there. 0.79 times 0.04 squared equals that number plus 0.0032 minus 0.016512. One of the nice things about writing down all these extra sig figs is, you know, if you make an error like that, it's pretty easy to deal with it. Yeah, so this gives me, so if I get a different number here, I get 140.09, 140.0909 meters squared, and that gives me raised to the half power 11.8. Yeah, okay, 11.836. Oh, I didn't screw it up earlier. Good, screwed it up this time. Anyway, so that's it. Any thoughts, questions, comments?
So what's outlined in red? Is that the control volume again?
Yeah, that's control volume.
Do we have to define that on a test?
I don't look for that. I probably should though. No. So what I'll be looking for is, does your approach make sense? So really, to me, there's two possibilities for control volume. One is really to just go large, you know. So this one is 1, you go large, and then what you've got is you've got a change in the mass within your storage. The other possibility is to go small in green like this, and then you've got an in here, you've got an in here, you've got an out here, and then this thing is, we said it was dropping, so we've got another in right here. Okay, and so basically you'd have 3 ins and 1 out. Okay, and that can also work. And in that case, what we do is, instead of having this term right here, we would have another, well, we wouldn't have that here. We would have, I guess we would call this rho tank. Rho tank times Q tank would be another in term.
Mm-hmm.
And in that case, the velocity would be this, the absolute value of this right here. So we would end up with the rho of the tank, which would be what, S3 rho water times Q tank, which would be 10 to the minus 4 meters per second, times that area, which would be pi over 4 times the diameter squared. Okay, and you should see that this term right here that I just wrote out, I'm just expanding this, all of that is contained right here. Okay, yeah. But this one had a negative sign because dHdt was negative. This one has a positive sign, but this one is on the left-hand side of the equation. So algebraically, they're exactly the same. Right, so this rho gets canceled right here. The area, you know, the dHdt, that's, oh wait, I forgot to put that in here, right? Oh no, this is the dHdt, sorry. This is the dHdt. It just has a different sign because in this one I'm considering it a velocity, and this one I'm considering it a derivative. And so it definitely has a sign here. And then this is the area, that's the area, and this is the S. So it's all the same. It's just a different way of thinking about it. So what I would be looking for when I grade it is, you know, did you follow a method that makes sense? And that's it.
All right.
Yeah, so either way works for me. Yeah, so then if there's no other questions, then we're done for the day because it's 12:11 and I only have 4 minutes, so I can't really do another one. But next week we'll probably work on the momentum equation. I'll just do momentum equation. To me is the hardest part of this course, but most of my students think the force on gates is the hardest part. So, you know, to each their own. So I guess
sounds good. Thank you.
All right, thanks guys.
Thank you.
Have a good day, and I will see you guys. Anybody needs any help, office hours later today.
All right, sounds good. Have a good one.
All right, take care of yourselves.
All
right, bye guys. Let's stop recording, then I'll sing songs. Let's see, I have one chat, close, I don't know about that. More.